Good morning, friends. So, this is my next lecture on the same topic, solutions. In last lecture, we seen the osmotic pressures, isn't it? Osmotic pressures means how that osmotic pressure is different in different solutions and their values, isn't it? And the experimental setup of that osmotic pressures. But today we are going to see that is depending upon depending upon values of osmotic pressure. The osmotic pressure is represented by symbol pi, isn't it? So depending upon the values of osmotic pressure pi, the solutions are classified into three criteria. Solutions are classified into three types. First one, that is the isotonic solution. Isotonic solution. Second one, hypotonic solutions. Hypotonic solutions. And third one, that is the hypertonic solutions. So depending upon the values of osmotic pressure pi, solutions are classified into three classes, that is isotonic, hypotonic and hypertonic solutions. If I said zero point 0.5 molar sucrose, zero point 0.5 molar sucrose solutions, and I want to classify these 0.5 molar sucrose solutions into these three classes depending upon the values of osmotic pressures. It is not a easy case, but it's not possible to just simply classify the 0.5 molar solution is whether isotonic or hypotonic or hypertonic one. Why? Because particular solution is not classified, isn't it? Just on comparing this zero point 0.5 molar sucrose solution to any other some solutions, then on comparison the depending upon the values of osmotic pressure, which solution has high value, which solutions have low value, or both have same values of osmotic pressure pi, this classification is carried out. So simply single solution cannot be classified. To classify this solution into out of these three classes, one more solution must be required for the comparison purpose. If I take 0.5 molar sucrose solutions and suppose 0.5 molar urea solutions, isn't it? Then these two solutions having same concentrations, experimentally it is determined that they also have same osmotic pressure. So they are comes in the class of isotonic solutions. That is, the isotonic solutions are those solutions which have same osmotic pressure. They have same osmotic pressure. That is 0.5 molar sucrose and 0.5 molar urea solutions. They are the isotonic solutions. So remember well, isotonic solutions are those solutions which have same osmotic pressure. जर osmotic pressure same राहत असेल तर त्या सोल्युशनला म्हणणार isotonic solutions, isn't it? Then hypotonic solutions, the solutions which have low osmotic pressure. Write the symbol low osmotic pressure in comparison with other solutions. In comparison with other solutions, दुसऱ्या सोल्युशनच्या तुलनेत जर एखाद्या सोल्युशनचा ऑस्मॉटिक प्रेशरची व्हॅल्यू कमी असेल तर कमी ऑस्मॉटिक प्रेशर असणाऱ्या सोल्युशनला काय म्हणणार? इट इज हायपोटोनिक सोल्युशन्स. If I consider example, suppose A solution has osmotic pressure suppose pi A, and suppose B solution has osmotic pressure suppose pi B, and if I write here pi A is greater than pi B, means osmotic pressure of A solution is more as compared with B. Therefore B solution which has osmotic pressure pi B, B solution is hypotonic with respect to A. Isn't it? म्हणजे ऑस्मॉटिक प्रेशरची व्हॅल्यू जर कमी असेल इन कम्पॅरिझन विथ अदर सोल्युशन, दुसऱ्या सोल्युशनच्या तुलनेत, तर त्याला आपण म्हणणार हायपोटोनिक सोल्युशन्स, isn't it? And in hypertonic solutions, the solutions which have high value of osmotic pressures or higher osmotic pressure in comparison with other solution. If I take the same example here, then I write that is the hypertonic A solution has more osmotic pressure than B solution. That's why A is hypertonic solution in this case. A is hypertonic solution in the case. So if both solutions are same, then it is isotonic. जर एका सोल्युशनचे ऑस्मोटिक प्रेशर दुसऱ्याच्या तुलनेत खूपच कमी असेल, हायपोटोनिक, आणि दोन सोल्युशनपैकी एका सोल्युशनचं ऑस्मोटिक प्रेशर खूप जास्त असेल, then it is hypertonic solutions. So it is simply classification depending upon their values of osmotic pressures. Okay. The next point we are going to study in the same point osmotic pressure, under the same point osmotic pressure. That point is the osmotic pressure and concentration of solutions. Osmotic pressure and concentration of solutions. Osmotic pressure and concentration of solutions. So as far as osmotic pressure and concentration of solution means, solution's osmotic pressure, how it is related with the concentration of that solution, how it is related with concentration of that solutions, that can be determined here. See, now for that purpose, you know, in the 11th standard, that is the ideal gas equation, ideal gas equations, and ideal gas equation is PV is equal to nRT. It is ideal gas equation or law, isn't it? PV is equal to nRT. It is the ideal gas equation, isn't it? Now in this case, it is applicable. P is the pressure of the gas, V is the volume of the gas, N is the number of moles of gas, R is the gas constant, and T is the temperature, isn't it? These are the terms. Now here in the solutions case, just instead of P, I replace here pi. Here P is the pressure of gas, here pi is the osmotic pressure of gas, a solution, osmotic pressure of the solutions. So means dilute solutions आणि गॅस हे दोघांच्यामध्ये जर कंपॅरिझन केलं तर गॅसियस कंटेनरमध्ये जसे गॅस मॉलिक्युल्स आतमध्ये दे आर इन रँडम इन मोशन, दे कोलाइड्स विथ इच अदर and they show some gas laws. That is the Boyle's law, Charles' law, Avogadro's law, isn't it? Ideal gas law, etc. By the same way, scientist Van 't Hoff, he showed that in a dilute solution also solute particles behave similar to that of the gas molecules, and also during that they also collide with each other and shows some solution laws. Like same Boyle's law, solution also shows Van 't Hoff Boyle's law. Like Charles' law, solution shows Van 't Hoff Charles' law. Like Avogadro's law, it shows Van 't Hoff Avogadro's law, isn't it? And similarly, the ideal gas laws, solution shows ideal Van 't Hoff ideal gas equation, and from that ideal gas equation just replace P by pi. One can write for ideal gas solution, it is pi V is equal to nRT. Where pi is the osmotic pressure of solution, isn't it? Just I write the terms. Pi is the osmotic pressure of solution, V is the volume in dm cube, means volume of solution in dm cube, N is the number of moles of solute. I write here solute. So as I write solute, so I make the number 2. Pi V is equal to N2RT. R is the solution constant, also called as a gas constant. Okay, solution constant or gas constant. It has similar values. That is 0.08206. That is the liter atmosphere per Kelvin per mole, or instead of liter dm cube is taken, and T is the temperature. So these are the, so instead of gas I write here solutions for the during case of osmotic pressure. So R is the solution constant, isn't it? At same value liter atmosphere per Kelvin, 8.314 joule per Kelvin per mole. Now in this case N2, if you observe, the N2 is the number of moles of solute. So if number of moles of solute, just if I rearrange this equation you call first, if I rearrange the equation first, it is clear. If you rearrange the equation first, then I can write here like this. V transport to this side, so pi is equal to N2 upon V into RT, isn't it? N2 upon V divided by RT, isn't it? Now if you observe this factor N2 by V, meaning of N2 by V, number of moles of solute used to prepare that solution. यूज टू प्रिपेअर दॅट सोल्युशन. म्हणजे सोल्युशन तयार करण्यासाठी त्या सॉल्वंटमध्ये वरून जे ॲड केलेले सोल्यूट्स आहेत त्या सोल्यूटचे नंबर ऑफ मोल्स N2 आहेत आणि टोटल सोल्युशनचं व्हॉल्यूम V. टोटल सोल्युशनचं व्हॉल्यूम V. सो इफ यू जस्ट कॉन्सन्ट्रेट ऑन धिस फॅक्टर, it is just a concentration term. It is simply N is the number of moles of solute, V is the volume of solution in dm cube. So mole per dm cube, that is the molarity. That is the definition of correct molarity. Molarity is nothing but number of moles of solute dissolved in 1 dm cube of solution or 1 liter of solution. So that's why molarity capital M is equal to N by V. Just only difference, instead of N I write here N2. That 2 represents the solute factor, isn't it? So replace this N2 by V by capital M. So pi is equal to M into RT. Pi is equal to M into RT. So this is the equation that gives the relation between osmotic pressure of solution and M. Capital M is the molarity of solution. Capital M is the molarity of the solutions. Now remember well here, M capital M, it is expressed in molar. It is expressed in concentration, expressed in molar means molarity, not in molal. Why? Because during the measurement of osmotic pressure qualitative properties, we fix here fix temperature value काय केलेली आपण फिक्स केलेली. टेम्परेचर व्हॅल्यू फिक्स जर असेल तर नॉट नेसेसरी टू यूज द टेम्परेचर इंडिपेंडंट कॉन्सन्ट्रेशन टर्म लाईक मोलॅलिटी. जर टेम्परेचरच कॉन्स्टंट असेल तर आपण इझिली मोलॅरिटी ही टर्म यूज करू शकतो. दॅट्स वाय हिअर मोलॅरिटी इज यूज्ड, not molarity. And this is the equation that represents the relation between osmotic pressure pi and concentration of solution in molar. Isn't it? Now next point, it is clear. Okay. The next point, that is the osmotic pressure. Its qualitative property completes. So just like lowering of vapor pressure, depression of freezing point, elevation in boiling point. Similarly, osmotic pressure has application, and I previously told you that all qualitative properties have same application, that they are used to determine molar mass of unknown solute. So application of osmotic pressure, that is used to determine molar mass of unknown solute. Used to determine molar mass of unknown solute. Now how it is used to determine molar mass of unknown solute? Now see here, if I write the equation pi V is equal to nRT, just I make N2RT. Pi V is equal to N2RT, isn't it? So just rearrange to retransfer this. Pi is equal to N2RT divided by V. N2RT divided by V. Now here, if you concentrate this N2, what is the meaning of N2? N2 is the number of moles of solute, isn't it? The number of moles of solute. So just relate the number of moles with mass and molar mass. Yes. So N2 is equal to W2 by M2, isn't it? W2 by M2. W2 is the mass of solute and capital M2 is the molar mass of solute. So W2 is the mass of solute in gram, suppose in gram, divided by capital M is the molar mass of solute. Molar mass of solute in gram per mole. That's why this gram cancel and this small n has unit moles, because per mole transferred it becomes moles. They become moles. The number of moles W2 by M2. Just substitute the value of N2 as W2 by M2 in equation. You call this equation suppose first. Then pi is equal to, instead of N2, W2 by M2. W2 RT divided by M2 into V. On rearranging to get M2 is equal to W2 RT divided by just pi into V. If you look at this equation, final equation, you call suppose star equation, the final equation, then in final equation, if you know all the terms of right hand side equations, W2 weight of solute, R it is the solution constant, its value is fixed 0.08205 liter atmosphere per Kelvin per mole or 8.314 joule per Kelvin per mole. is the temperature of that experiment. म्हणजे ऑस्मॉटिक प्रेशर आपण करत असताना जो एक्सपेरिमेंटल त्या रूम लॅबची टेम्परेचर असणार तो फिक्स, isn't it? Pi, it is determined of that solution by using the apparatus or instruments used to determine the osmotic pressure, and V is the total volume of solution. So if you know all these terms, one can calculate capital M2, that is the molar mass of unknown solute, can be determined. Molar mass of unknown solute can be determined. So this is one of the most important applications. Along with this application, it has one more application in our day-to-day life. In our day-to-day life, generally we use the purified water, isn't it, for drinking purpose. But if you consider the purified water, then on that apparatus, there is a one symbols are used. That is the UV, RO, etc. So that RO stands for reverse osmosis. Reverse osmosis. What is reverse osmosis? What is the case of reverse osmosis? RO. What is regular osmosis? In osmosis process, in osmosis concept, solvent molecule flows from dilute solution to concentrated. Solvent molecules are passes. Means if I made two compartment here, suppose, and they are separated by semi-permeable membrane. Here suppose A compartment and B compartment. A compartment suppose solvent is there, and B compartment suppose solution is there. Okay, salt solution is there. Then in regular osmosis, what happens? In regular osmosis, the dilute solution means solvent molecules from A compartment, it moves to B compartment. It is in regular osmosis. It is a regular osmosis technique, that is the flow of unidirectional and continuous flow of solvent from a dilute solution to concentrated solution. म्हणजे सॉल्वंट इकडून इकडं पास होणार ऑस्मॉसिसमध्ये. But if I observe the reverse osmosis, now if I apply a pressure on solution side, if I apply a sufficient pressure P on solution side, isn't it, just greater than osmotic pressure pi, ह्या प्रोसेसमध्ये ऑस्मॉटिक प्रेशरची पायची व्हॅल्यू जी असणार आहे, ह्या ऑस्मॉटिक प्रेशर पायच्या व्हॅल्यूपेक्षा जर एक्सटर्नल प्रेशर P एक्सटर्नल ऑन सोल्युशन साईडला जर इन्क्रीज केलं, वाढवलं, तर होणार काय? ड्यू टू इन्क्रीज इन द एक्सटर्नल प्रेशर ऑन सोल्युशन साईड, व्हॉट हॅपन्स in this solution side, solution in the sense it have both solute as well as solvent, but due to increase the pressure of solution compartment, what happens? Through this semi-permeable membrane, solvent molecules travels or they pass into solvent through this semi-permeable membrane, because pressure is increased on solution side, and here it allows the semi-permeable membrane allows only solvent. That's why solute remains in the B compartment and only solvent moves into A compartment, isn't it? So in this way, it is, suppose B compartment I write rather impure water, and in A compartment I write here pure water. So in this way, by the same way, in purify instruments which are used in water purifier, in this case the impure water ultimately converts into pure water, and this pure water is used for drinking purpose. That is from impure to pure. So this is one of the most important application of osmotic pressure, the reverse osmosis, isn't it? So next lecture we see the last bit of that topic. Okay, good day.